When an autoregressive language model predicts the next token, it is solving a mathematical problem framed a century before the hardware existed to run it. The logic used to generate text step by step was codified in 1900 using pen and paper. This is Andrei Andreevich Markov. Every modern language model, from GPT-2 onward, is a direct descendant of the probability theory he established while working in St. Petersburg. In 1913, Markov performed a manual experiment on 20,000 letters of Alexander Pushkin's Eugene Onegin. He stripped the text of punctuation and spaces, arranging the characters into grids to track the frequency of specific sequences, specifically 1,104 vowel-to-vowel and 3,827 consonant-to-consonant pairs. By computing the probability that a vowel follows a consonant, Markov recorded the first statistical model of natural language. The conditional distribution an LLM computes at each step belongs to this same family, symbol by symbol and history conditioned. The text that established these methods, the Calculus of Probabilities, was published in 1900. This predates his work on dependent sequences, the famous Markov chains, by 6 years. Before he could analyze how sequences depend on their history, Markov first had to build a rigorous framework for analyzing independent probabilities. In 1900, St. Petersburg was the center of a specialized mathematical movement. Markov was a student of Pafnuty Chebyshev's. They formed the Russian School of Probability, an intellectual circle that prioritized strict formal proof over the heuristic guesses common in 19th century statistics. At the time, probability was an erratic field. It lacked a cohesive axiomatic foundation and was frequently used by statisticians to justify sloppy reasoning or poorly supported claims. Markov wrote his 1900 book to correct this. He sought to derive classical theorems purely from first principles, ensuring that probability could be treated as a hard, structural science. He began by defining an event with absolute precision. He demonstrated how mutually exclusive cases behave, and crucially, how those behaviors shift depending on what an observer knows. His abrasive insistence on mathematical rigor transformed probability from a loose experimental tool into the logic required for future computational models. Markov's definition of independent quantities revealed that independence is not an inherent physical property. It is a state determined by the observer's information. He describes two vessels. Vessel C contains only black balls, while vessel D contains a mix of A white and B black balls. If you know vessel D was selected, drawing a ball is an independent event. The probability of pulling a white ball is A over A plus B, and returning the ball resets the system for an identical second draw. But if the vessel is unknown, the math changes. Drawing a white ball instantly proves vessel D was chosen, since vessel C has none. That single observation locks in the conditional probability for every subsequent draw, ending the independence of the trials. This isolates a core principle for machine learning. An observation's parameters and the system's prior state determine whether variables can be treated as independent. In Chapter 2, Markov addresses repeated trials. He asks, what is the probability that event E occurs exactly m times across n independent trials? Attempting to solve this through brute force counting is impossible at scale. Tracking permutations across thousands of trials creates a tree that expands exponentially, making direct calculation unmanageable. Markov's solution was to encode these discrete probability states as coefficients in a polynomial expansion. By shifting from manual counting to algebraic multiplication, he created a method that allowed probability calculations to scale without the need to track individual permutations. This is his generating function. Here, P is the probability of success, Q is failure, and the Greek letter Xi is a placeholder variable used to track each successful outcome. Markov used a recurrence relation where each new trial simply multiplies the existing polynomial. As the terms expand, the exponents of Xi automatically increment to track the total number of successes. To find the exact probability of m successes, you only need to extract the coefficient attached to the exponent m. He built an algebraic sorting machine, translating the chaotic branching of events into a cleanly ordered sequence. Chapter 5 explores what happens when the number of trials reaches toward infinity. At this scale, calculating exact factorials for coefficients becomes a mechanical impossibility. Even for a human computer in 1900, the numbers become too large to process. To bypass this, Markov derived a version of Laplace's theorem, which replaces these discrete, impossible factorials with continuous approximations. Using Stirling's approximation, he swapped out the factorial terms for manageable exponential functions. This transition from factorials to exponentials proves that discrete, random events map onto smooth, continuous curves as they accumulate. When the limit of the trials is taken, Markov transforms the sum of individual probabilities into a continuous Gaussian integral. This integral describes the symmetrical bell curve. It provides the probability that an event falls within a specific range of the expected mean. Markov used this integral to prove Bernoulli's theorem, the law of large numbers. This guarantees that as the number of samples increases, the average of the results will stabilize and move closer to the true expected value. He provided the mathematical proof that while an individual event is unpredictable, millions of events dissolve into predictable certainty. This proof that variance shrinks as samples increase is the mechanism that allows modern neural networks to learn. Training an LLM is the process of adjusting billions of weights to estimate the true probability distribution of human language. Because language is high-dimensional and complex, small data samples result in noisy, erratic predictions. Models require the massive scale Markov described so that the chaotic deviations of individual tokens average out, allowing the network weights to converge on stable predictions. Markov mapped these laws of convergence in 1900, at a time when the fastest available processor was a well-sharpened pencil. By establishing these foundations for independent variables, he created the toolkit he would use 6 years later to invent Markov chains, the history-conditioned logic used in modern GPTs. Andrei Markov established the statistical architecture of artificial intelligence nearly a century before humanity built the machines capable of running it.